Okay, on page 360 of your book here for section 4.2, there's a couple of ideas here that I want to talk about here before we start talking about angles and trigonometric functions. We have a couple of things from geometry that are going to help us here to develop this idea of using these trigonometric functions. And one is we'll call similarity. Remember, in similarity in geometry, we're two shapes that have the same shape but different size. Okay? But ultimately their sides and the sides are going to be proportional to one another. And with that said, what we're going to look at today is what we call right triangle trigonometry. Okay, we've done some right triangle trigonometry in all three classes we've had so far in algebra, geometry, and algebra 2. Okay, and today we're going to take a closer look at those, review some things that we already know, and then work some problems involving right triangle trigonometry. So, first thing that we want to make sure we're clear on is that when we have an angle, if we put it in standard position, okay, that means that the tail of the angle is going to be at the origin, and the measurement of the angle is going to be always measured from the positive x-axis. And this is kind of what I talked about yesterday. This is our normal measuring from the positive x-axis. When we talked about bearings yesterday, bearings were measured clockwise from the positive y-axis, if you will. So that's completely different than what we're talking about here with this idea of right triangle trigonometry. Okay. All right. So with that said, we're going to look at the 6 trigonometric functions. So these are the functions themselves. And again, we've seen especially the left 3 before in our previous classes. But what it boils down to is anytime that we have a right triangle, and in this case it's triangle ABC, okay, labeled by the vertices, okay, there are going to be always 6 true ratios, okay, that compare, okay, one of the 2 acute angles, and we can write these for either angle. We're going to use this as our angle in question at this point. Okay, we could name this angle something different and write functions for it also, but we're going to do it based on this angle and this triangle, recognizing that for that angle, the side, or the leg, if you will, that is a part of that angle is going to be the adjacent leg. Okay? The leg that is not a part of it, that's across from it, if you will, is going to be the opposite leg. And of course, the side that's across from the right angle is always going to be the hypotenuse, no matter what. So we might say, well, how come this one's not adjacent? That one's touching the angle also. But remember, it can't be adjacent because it's already the hypotenuse. So identify the hypotenuse first, and then you can identify the 2 legs. And again, all of this is in relationship to this angle. Okay, would these labels change if we were talking about this angle? Yeah, well, except for the hypotenuse, that wouldn't change. But ultimately, if we were talking about angle B, then that would be the opposite side, and that would be the adjacent side. Now, okay, what we know about these trig functions is the following. Okay, is that when we look at this sentence right here, okay, the sine of the angle, okay, is equal to the ratio of the opposite side over the hypotenuse. Okay, which is convenient because if we knew both the opposite and the hypotenuse, if we knew those lengths, then we'd only have one variable in this sentence and we could solve it to find theta. Or if we knew theta and we knew, say, the opposite side, okay, then there'd only be one variable, which is the hypotenuse, and we could solve for that variable. Okay, or finally, if we knew the angle and the hypotenuse, then the only variable left would be the opposite side, and we could find that. So what we're going to be able to do with these trig functions, number 1, is to solve triangles. Okay, it will help us solve, and in this case, of course, they have to be right triangles, because none of this is true unless they were dealing with a right triangle, keep in mind. Okay, but ultimately, it's going to allow us to solve triangles, find missing sides, and find missing angles. So in general, if the directions say solve this triangle, that means find all the missing sides and find all the missing angles. So ultimately, how many things are we looking for then? How many sides and angles do we have in a triangle? There's 3 apiece, so we should be looking for 6 items total. And obviously, if it's a right angle, we already know one of the angles. One of the other tools we have is if we do know theta, okay, wouldn't we also know b over here? Because what do we know about from geometry? That triangles, angles have to add up to be 180. Okay, so we would know that. And any missing side, if we only had one side, we would not be able to use the Pythagorean theorem like we used in our warm-up, okay, because one side wouldn't do it. But if we had one side and we had an angle, then we could use one of these trigonometric functions to get the work done. Okay. So ultimately, what we need to make sure we know is which ratio goes with which trig function. Okay? We need to know that the sine is always going to be the opposite over the hypotenuse. Cosine is going to be the adjacent over hypotenuse. Tangent is going to be the opposite over the adjacent. And then the other three trig functions are going to be the reciprocals of the ones on the left. Okay, the cosecant is always going to be the reciprocal of the sine, hypotenuse over opposite. Secant's the reciprocal of the cosine, and cotangent's going to be the reciprocal of the tangent. Now, I usually remember those ratios by thinking of this word, SOHCAHTOA. And you may have seen that before. Ultimately, this just helps us remember which ratio goes with which function. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Okay? And you don't really need to have to memorize these, okay, because ultimately they're just going to be the reciprocals of the ones to their left. What you do need to make sure you know, cotangent and tangent, those are pretty easy to connect in your mind. What I usually do here for sine and cosecant, cosine and secant, okay, you would think that these two would be reversed, wouldn't you, the way they're spelled? They're the same letters. Wouldn't that be nice if they were the same letters? But they're not. So keep in mind that they're always going to be opposites. Sine and cosecant go together. Cosine and secant go together. Fair enough? Okay. All right. Questions so far? All right. Now, one of our main emphasis is going to be being able to evaluate trig functions at particular angles. Now, there's going to be three special angles that we're going to need to have memorized, okay, starting today. Okay, and the three special angles are going to be from our special triangles we learned about in Algebra 2. And that's a 45, 45, 90 triangle, and a 30, 60, 90 triangle. Okay, all right. And what it boils down to is that when we have a 45, 45, 90, we'll start with that one. Okay, the relationship between sides is always the same. Okay, they're always in a ratio of the legs are 1 to 1 because notice they're across from a 45. They're both across from the same size angle. So it shouldn't be surprising that the side lengths are the same. That was one of our geometric properties we learned. Okay, so if these two are both 1s, then this is going to be 1 radical 2. Okay, okay, had these both been 3, let's say, then that would have been 3 radical 2. Okay, ultimately the relationship is, in general, x, and then x radical 2. So if we know one leg of a 45, 45, 90, the other leg is the same, the hypotenuse is always the leg times radical 2. So that's the relationship when we have a 45, 45, 90. And so what that allows us to do is it allows us to find the answer to what is the sine of 45 degrees in an exact manner. Okay, your calculator has a sine command on it where you could type in sine of 45 and get an answer, but it's going to be a decimal. We want to have the exact answer when we're dealing with 45 because it's a special angle. Okay, so let's go ahead and develop the answer to that right here. Sine of 45, if we look at the 45, we'll use this one. It really doesn't matter which one we use. But sine is equal to the opposite, which would be 1, over the hypotenuse, which is radical 2. And so that is the answer to the sine of 45, except for in trigonometry we don't leave the radical on the bottom. So we would want to multiply by radical 2 over radical 2, and we get radical 2 over 2. So the sine of 45 degrees is radical 2 over 2. That is a number and a fact that you need to memorize starting today. Okay, and I'm going to give you some good news. There's only 3 numbers you have to memorize. Okay, and one of them is radical 2 over 2. Fair enough? Okay. Let's do that for cosine. Cosine of 45 degrees here would be adjacent, which would be this one, over the hypotenuse. And so if I do the same thing here, then what is the cosine of 45? It's also radical 2 over 2. So that's more good news. The cosine and sine of 45 are both the same. They're both radical 2 over 2. And then the tangent of 45 is going to be the opposite over the adjacent, which is 1 over 1, which equals 1. Okay? Questions so far? Alright, so again, really the only one that you have to memorize is this one, because that's going to be, I mean, tangent, you can make that triangle and figure it out pretty easily. Let's do cosecant then. How about the cosecant of 45 degrees? Okay, we don't have to memorize this because what are we going to do with sine? Sine and the cosecant are just reciprocals. So I would do it in this form. Remember, this was the original form of sine of 45, right? So if I flip that, isn't the answer just simply going to be radical 2? And what about the secant of 45? Radical 2 also. And how about cotangent of 45? If I go flip 1, it's going to be 1 over 1 still. It's going to be 1. Okay, questions on developing those? Okay. All right, so let's take a look next then at our other special triangle, which is a 30, 60, 90 right down here. Okay. And the relationship on a 30, 60, 90 triangle, okay, which would be this one right here, okay, essentially comes from taking an equilateral triangle and dropping a perpendicular down the middle of it. Okay, but the relationship is going to be the short side, which is across from the 30, is 1. The long side, which is across from the, the hypotenuse right here, is going to be double that. Okay, and then the long side, which is across from the 60, is going to be radical 3 times it. So we're going to use these numbers because that's the most basic it can be, with a 1 for a short side. But in general, the relationship is this. It's if the short side is x, okay, the hypotenuse is 2x, and the long side is x radical 3. Okay. So if we knew that that short side was 10, then the hypotenuse would be 20, and the long side would be 10 radical 3. Okay. Now, with that said, let's see if we can figure out the sine of 30. Okay. So let's look at 30. 30 is right here. 30's opposite would be 1, and the adjacent would be, the hypotenuse would be 2. So therefore the sine of 30 would be 1/2. And this is one that's pretty easily checked with your calculator if you make sure you're in degree mode, which I'm currently not. So I'm going to change mine to degree mode. And then go ahead and hit sine 30. I get 0.5, which shouldn't be surprising because we know that based on this triangle, it had better be 1/2. Okay. Cosine of 30 is going to be adjacent, which is radical 3, over the hypotenuse, which is radical 2. Okay. And finally, tangent 30, okay, is going to be opposite over adjacent, so 1 over radical 3. And I would not leave it like that, of course. I'd make that radical 3 over 3. And so those would be the sine, cosine, and tangent of 30 degrees. Okay. Now, of course, the reciprocals of those, the cosecant, secant, and cotangent, we can find by just flipping those. Okay, so I'll leave that part up to you to write down. And then I want to move to the 60s. The 60 here, the sine of 60 is going to be opposite over hypotenuse, which is radical 3 over 2. Cosine of 60 is going to be adjacent over hypotenuse, which is going to be 1/2. And then the tangent of 60 is going to be opposite over adjacent, which is going to be radical 3. Now, a few minutes ago I mentioned that you're going to need to memorize 3 values today, right? Okay, I told you already the first one's the radical 2 over 2, which is the value for sine and cosine of 45. Okay, the other 2 are these 2. Okay, and those are the only 3 values you really need to memorize. Okay, you need to memorize that the sine of 30 is 1/2, okay, and the cosine of 30 is radical 3 over 2. Now remember, keep in mind that you really don't have to memorize those because you could make these similar triangles and figure it back out again. Okay, but if you know those 3 values, okay, and we're going to relate this to the circle in just a minute. Okay, if you know those 3 values, you should be able to come up with the sine, cosine, and tangent. Okay, and then if you know those, you can find the other 3 because they're just the flips. Okay, you should be able to find the sine, cosine, and tangent of any angle, okay, that's a multiple of 30 or 60 or 45. Okay, we're going to see how we do that in just a minute. Okay, so those are the 3 key values, though, that you need to have in your mind. Okay, Now, like I said, do you have to memorize that sine of 30 is equal to a half and that sine of 60 is equal to radical 3 over 2? No, because I'm going to show you a way you can figure it out real quick without having to memorize which one's which. Okay. At some point, you'll use it enough that you probably will know, though. All right. So, that said, so again, the three key values you need to memorize are radical 2 over 2, radical 3 over 2, and 1/2. Okay. Those are going to be the answers to any sine-cosine problem that involves those three angles. Okay. Now, there's one other relationship here I want to talk about with tangent, because I haven't told you need to memorize this. Okay, because what it boils down to is that tangent of theta is also equal to sine theta over cosine theta. Okay, and this is an important relationship, because as long as you know the sine and the cosine, then couldn't you divide those two values and find the tangent, as opposed to memorizing the tangent values? Absolutely. Okay, one less thing to memorize if you know what tangent is equal to, because then you can just take that divided by that, and guess what it gives you? That.